Hey everybody, it's Thursday, March 18th, and as you can see here in the aim today, our goal for today's video is all about how we can use our understanding of energy conservation and rotational motion to solve problems. Now, we've got a lot to get into today, so let's just get right into it. The first thing we're going to talk about is the problem I assigned to you at the end of yesterday's video. Just to give as quick of a recap as possible, you all did this, so I'm sure you remember. But in yesterday's video at the end, we took a look at a ramp rolling problem. And we saw here that we had a disk starting from the top of a ramp with a height of 30 centimeters. And the question was, what is the speed of the disk when it gets to the bottom of the ramp? And we calculated that speed as 1.98 meters per second. And then I asked you, well, now we want to go ahead and do this calculation, but instead of for a disk, to do this calculation for a marble instead. And that was what I assigned to you yesterday, to repeat the calculation that we did for the disk, but instead to do it for the marble, and to see if it comes out with a larger speed, the same speed, or a smaller speed. And so what I want to do here first is just show that calculation. And so I asked you to derive an expression for the final speed of the marble and then solve the equation for the marble's final speed. And so your calculation should have looked a little something like this. The first thing I'll write here is just the information about the marble. We said here the radius of the marble was 0.015 meters. We said that the mass was 0.012 kilograms. Now it said, I think that it was 1.5 centimeters. So move it back twice. That's your radius measurement. And I think it said the mass was 12 grams. And so if we move that back 1, 2, 3 spaces, then we get it in kilograms. As you hopefully realize now, those two numbers don't matter at all for the final answer, but I'll include it here just because you might have yesterday. We need our delta y here, the height of the ramp, 0.30 meters. And of course, we're going to need g as well, 9.8 meters per second squared. And we are looking for the speed of the marble when it reaches the bottom. Now, something that you're going to need, I'm sure you all realized, is the equation for the rotational inertia of the sphere. Remember, a marble is a sphere, and so that's 2/5 mr squared. And so the basic conservation of energy framework for an object that is rolling down a ramp is going to be the same every single time. We say the initial gravitational potential energy is eventually converted to the final translational kinetic energy and the final rotational kinetic energy. When an object rolls down a ramp, it is both rotating, and so it has rotational kinetic energy, and it's translated down the ramp, and so it has translational kinetic energy. And so we have here, once we sub in the equations, mg delta y equals 1/2 mv squared, and I'll write a v final squared, plus 1/2 I omega final squared. Now, of course, this version of the equation is no help. And so as we said yesterday, and this is kind of what I mean by it's the same thing every time you solve one of these, what you need to do is you need to make your substitutions for I, sub in the equation for the rotational inertia of the object, and then make your substitution for omega by subbing in the equation for omega. And you don't have to write that up here, but I'll just write it up here as a reminder. It's very important for you all to know that omega is equal to V over R, because you're going to have to do that substitution always when you're doing these problems. And so when we make those substitutions here, the next line is going to look a little something like this. We'll have mg delta y equals 1/2 mv final squared plus 1/2. For I, we'll sub in 2/5 mr squared. And for the omega final squared, well, if omega is v over r, then omega squared is going to be v squared over r squared. And I don't know about you, I didn't quite show this in the video yesterday, but I'm making a proclamation now that extends to every other time you ever have to solve this. There's no point in showing the work for v over r squared is v squared over r squared. I'm going to go out on a limb and assume that's pretty obvious to all of you. And so if you want to plug it in here, that's totally fine with me. Now, this is one of the most consequential lines of the work conceptually here, because if you remember in the beginning, I said this number and this number, well, they don't really matter for this problem. And if the question is, well, why not? Well, here, because the rotational inertia equation will always take the form of something times mr squared, and because the omega will always be v over r, once you square the omega, that'll have an r squared. Those r squareds will always cancel. I want you to pay very close attention to my usage of the word always here. The rotational inertia equation always takes the form of something times mr squared. If it is a disk, it is 1/2 times mr squared. If it's a sphere, it's 2/5 times mr squared. If it's a hollow sphere, I think it's 2/3 mr squared. Just check the sheet, you'll see it. If it's a hoop even, it's 1 times mr squared. And so there'll always be an r squared in that term. There'll always be an r squared here, and those two things will cancel. When you rewrite that line, if you wanted to do it here, you would realize that this term has an m, this term has an m, and this term has an m. And that means the masses cancel as well. And so what we're left over with is g delta y equals 1/2 v final squared plus, and now we just need to do some math with these fractions here. When you are multiplying fractions, you multiply the numerator, multiply the denominators. You get 1 times 2 is 2, 2 times 5 is 10. And that ends up being 2/10 v final squared. And I should really put a v final here too, probably. It's not a huge deal, but just to keep everything the same. And so now we just have to combine these terms on the right-hand side because it's some fraction times v final squared. Now, if you wrote here 1/5 v final squared, that's cool. Having said that, when you add these fractions, the least common denominator is 10. And so there's not really too much reason to do it. It's not that big of a deal. But since 1/2, if you're going to put it in terms of tenths, would be 5/10, then you have 5/10 vf squared plus 2/10 vf squared, and 5 plus 2, of course, is 7/10. So you get 7/10 v final squared. And now to solve this for the final speed is easy. You just move the fraction over to the other side. And of course, when you move it over to the other side, it flips over. And then you just take the square root. So we get v final equals, we got to flip that, 10/7 times g delta y. And then we take our square root. And that's it. It's a pretty simple equation. And so we have here 10/7 times g, 9.8 meters per second squared, times delta y, 0.30 meters. And when you do that math, making sure you're typing the fraction into your calculator correctly and making sure you're taking the square root, we get 2.05 meters per second. And that answer is pretty cool. Because specifically at the end of yesterday's video, before I told you I actually wanted you to solve for this speed, I told you that I wanted you to make a prediction about how the two speeds would compare. And basic understanding of rotational motion tells us that rotational inertia is a measurement of an object's resistance to rotational acceleration. And so the very fact that a disk's rotational inertia is 1/2 mr squared and the marble's rotational inertia is 2/5 mr squared means the marble, or the sphere here, has a smaller rotational inertia. And if it has a smaller rotational inertia, that means it's easier to rotate, and thus it should make sense that it reaches the bottom with a larger final speed here. And of course, when you actually look at the calculation here, it does have a larger final speed. The final speed of the disk that we calculated yesterday was 1.98 meters per second. And this one is clearly larger at 2.05. Pretty good. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so now I want to use this part of the video, now that we've done two of these calculations for basically the same setup, identical objects with the same mass and the same radius, just a different shape. I want to take a couple of minutes to just really investigate what happened a little more and suss out some key concepts. And so the first question that we're going to ask here is, using the two equations for the final speed of the objects, the disk and the marble, how can we determine what ultimately affects the final speed of the rotating object? This is something really important for you to think about. I actually want you to pause the video here and think about this. Looking at the two equations we had for the final speed, what ultimately affects the final speed of the rotating object? Take a second to pause this video here and think about that, and when you hit play, we'll go over it. Now, I'm sure some of you are looking at this equation for the disk or the marble, And you're saying, well, that kind of looks like just a straight up potential to kinetic energy transformation. And as we said, for those problems, the only thing that matters is the height. The height determines the speed. Well, it is absolutely the case that the height plays a key role in determining the speed. But something else matters. And so what I'm going to write here is a very important note. The final speed of a rotating object rolling down a ramp is dependent on the height and the fraction in front of the mr squared in the rotational inertia equation. As I mentioned before, the rotational inertia equation is always going to take the form mr squared times something. What ultimately determines how fast it will be moving at the bottom of the ramp is that something, which the mr squared is multiplied by. As I wrote here also, what's very important to know is that if it's a lower fraction, that's going to end up giving the object a higher final speed. And that should make sense, because if the fraction is lower or smaller, then that means the rotational inertia is smaller, which means the object is easier to rotate and thus has a higher final speed. Now, before I ask you to pause here and write that down, we might as well just also say, for further clarification, note, since the fraction gets flipped when we solve for the speed, right? Because we have to divide over to the other side, and when we divide that fraction over to the other side, I'll show you what I'm talking about here, because when we have to solve for v final, we have to divide both sides by 7/10, and then the fraction just ends up getting flipped here as 10 over 7. When we solve it for the final speed, that lower fraction in front of the mr squared will end up producing a larger final speed, specifically because the fraction gets flipped. Notice 2/5 is smaller than 1/2. But when you flip over 1/2, you get 2. And when you flip over 2/5, you get 5 over 2, which is 2.5. That's the point. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now we want to ask some other conceptual questions about what we just saw. I really do think it's important. I want to say this before I show the first question. I really do think it's important for you to listen to what I'm saying and pause the video when I'm telling you to pause the video and actually think about it. Because if you do that, you will be able to identify the flaws in your thinking. And if you identify the flaws in your thinking when you're first answering these questions, it'll make it a lot more likely that you won't make mistakes when you're doing these kinds of things later on. And that, of course, is really important. So let's take a look at a question. First question, interesting. How do the total kinetic energies of the disk and the marble compare? How do the total kinetic energies of the disk and the marble compare? Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, a perfectly reasonable answer to this question would be, well, the marble is going faster, so it has more total kinetic energy. No? It's a reasonable thought. But ultimately, since the total initial gravitational potential energy of the objects is the same, because they are the same mass and they start up at the same height at the top of the ramp, both objects will end up with the same total kinetic energy. That is a dirty, dirty trick. It's important to realize that they are going to ask you that kind of question with one thing and one thing in mind, which is the question is designed to trip you up. Conservation of energy carries the day, always. They start with the same gravitational potential energy, so that means at every single point in their motion, they have the same energy. Really important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And so a clear question is, well, wait a second. If the objects have the same total kinetic energy, then why don't they end up with the same final speed? It's a weird question. But we can figure it out if you just take a look at the equations. Since the objects have the same total kinetic energy but have different rotational inertias, the distribution of kinetic energy among the rotational and translational forms is different. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And so to make the point here perfectly clear, since they start at the same height, they'll have the same gravitational potential energy, meaning they'll have the same total kinetic energy at the bottom. Since each object requires a different amount of energy to rotate, how the energy is distributed between rotational and translational kinetic energy will be different. You all don't have to think about this the way that I think about it. But I think personally, for myself, a really easy way to think about it is to think about the gravitational potential energy having to be used up to get the thing to rotate. Because I hope everybody realizes the only reason a rotating object is moving translationally is because of the rotation. An object that is rotating doesn't move until it begins rotating. So if the object is harder to rotate, then it's going to take longer to move a certain distance. Like, think about it. If both of these objects have the same radius, that means they have the same circumference. And so when they complete one rotation, they will travel the same distance. That distance will be equal to their circumference. The point is, if they're traveling a distance that is equal to their circumference, but it's taking one of them longer to travel that distance because it's harder to rotate, then that's why we are saying it ends up going slower. Because if they're both traveling the same distance, which we'll just say for one rotation is equal to their circumference, but it's taking the disk longer to do that because it's harder to rotate, well, then that's why we're saying it's going slower, because it's taking more time to travel the same distance. To me, that really makes sense, that the gravitational potential energy has to be used up to just get the thing to rotate. And because so much of that energy has to be used up to just make the thing turn, less of it can be used to translate it down the incline. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I know at the end of reading what's on the slide here, I just made a big point, and so I actually want you to summarize that here. Notice the question here, just a general question. How can we use information about the object's rotational inertia to describe the transfer of energy in this problem for the marble and the disk? The idea is, while the disk reaches the ramp's bottom with a speed of 1.98 meters per second, an identically sized marble finishes at 2.05 meters per second. The marble, a sphere with a rotational inertia of 2/5 mr squared, has a lower rotational inertia than the disk. The disk has the rotational inertia of 1/2 mr squared. Since the disk has a higher rotational inertia, more of the original gravitational potential energy has to be used to get the disk to start to rotate, because it's harder to rotate, which means that less of that original gravitational potential energy is available to facilitate linear motion. That's why it has a lower final speed. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, now we've got a little bit of a weird question to ask. But since they love these kind of questions on the AP test, I want to ask you a sort of modified version of it now. Suppose we repeated the previous problem. Now notice this is going to be for the third time. We did it with the disks, then we did it with the sphere. Now we're saying we're repeating the previous problem, but instead of a sphere or a disk, we're just going to slide a block down the ramp, which is unable to rotate. It's got the same mass, though. It's got the same radius. I guess we could just say like the length of the block is equal to the diameter of the disk in the sphere. I want you to predict, using concepts only, how these three speeds should compare. Now, we already know that the speed of the disk is smaller than the speed of the sphere. The question is, where does the block fit in with that ranking? Take a second to pause this video here and think about it. Make a prediction. Is it going to be faster? Is it going to be slower? Is it going to be somewhere in between these two? And when you hit play, we'll move on. All right, I don't want to give away the game here. Calculate it. Pause the video. calculate what the speed of a block would be at the bottom of a 30-centimeter high ramp. See if it confirms your prediction. When you're done with that calculation and you've obtained a number for the final speed, hit play and we'll go over it. All right, now the problem says the block has the identical dimensions as the sphere and the disk. So let's just go ahead and say the mass of this block is 0.012 kilograms. The height is 30 centimeters. So we'll write delta y as 0.3 centimeters, or sorry, 0.3 meters. G, of course, is 9.8 meters per second squared. And we're looking for V final. Obviously, what's different about this problem is that the gravitational potential energy this thing has in the beginning is going to be all translational kinetic energy at the end. Notice here I did not put that subscript on there. If you don't have both kinds of rotational kinetic energy, you don't need to put the subscript on our good old-fashioned 1/2 mv squared. Because rotational kinetic energy is very specific, you should put the subscript R on that just because that's the second one we looked at. Anyway, you have mg delta y equals 1/2 mv final squared. Of course, as is always the case, the masses cancel, and we get v final equals the square root of 2g delta y. And so when we plug those numbers in here, we get 2 times 9.8 meters per second squared times our change in height, which is 30 centimeters or 0.3 meters. And when you do that math, plugging in all your numbers and making sure you're taking your square root, you end up getting a final speed 2.42 meters per second. Now, the big question is, was that what you were predicting? I hope so. That makes a heck of a lot of sense. If a block slides down the ramp next to the marble and next to the disk, it'll finish with a speed of 2.42 meters per second, which is even faster than the marble or the disk. That makes sense. Since none of the original gravitational potential energy is being used to make the object rotate, all of the original energy is being used to be able to make the object move linearly. And that is why it's faster. Take a second to pause this video here and write down this note, as well as this solution if you're missing any part of it. And when you hit play, we'll move on. All right, now we're going to move on to the sheet here that was attached to the post on Google Classroom for today. But before we do that, I just want to point out the structure of the calculation really gives away what's going on here. As you saw with the block, what all of these equations have in common is a g delta y under the radical. The difference is the number. The number in front of the g delta y for an object that's not rotating is always going to be 2. That's always going to be the case, and that comes from this 1/2 in the kinetic energy equation. Notice when we did it for the marble, we ended up getting a fraction that was 10/7. So notice that's bigger than 1, but it's not quite 2 because 2 would be 14/7. It's about 1.4-ish. And if we did that for the disk, which we did the other day, we got 4/3 g delta y. And of course, 4/3 is about 1.33333. And so the point here is the fraction in front of the mr squared is ultimately going to determine this number that's in front of the g delta y. And that will ultimately determine how the speed of the thing compares to the speed of just like an ordinary block, which is not rotating. And they love to ask questions like this on the AP test. All right, let's take a look at the problems on the rotational motion problem-solving worksheet here attached to the post for today. The first problem on this sheet is from the Tipper's book B6RT14. It says rolling objects released from rest, time down ramp. 4 objects are placed in a row at the same height near the top of a ramp and are released from rest at the same time. The objects are a 1 kilogram solid sphere, a 1 kilogram hollow sphere, a 2 kilogram solid sphere, and a 1 kilogram thin hoop. All 4 objects have the same diameter, and the hoop has a width that is 1/4 its diameter. The time it takes the objects to reach the finish line near the bottom of the ramp is recorded. The moment of inertia for an axis passing through the center of mass for a solid sphere is 2/5 mr squared. For the hollow sphere, it's 2/3 mr squared. And for the hoop, it's mr squared. Now, I just want to address something very quickly because people were asking this in the Zooms yesterday. The rotational inertia reference sheet that I gave you is from the textbooks that are featured in our packets. They're not going to give you one of those on the AP test. That said, they are going to give you information like this within the problem. If they don't, you can still figure out how the rotational inertias compare, because it should make sense to you that the object with the most mass concentrated farthest away from the pivot point is going to have the highest rotational inertia, and that's the hoop. Of course, the hollow sphere comes next, because the very fact that it's hollow means it has a lot of mass concentrated far away from its pivot point. And then, of course, the sphere is least because, well, its mass is distributed uniformly throughout the sphere. So this particular question here says, rank the 4 objects from fastest, and they specifically say by fastest here, they mean shortest time, down the ramp to the slowest, and then explain your reasoning. I want you to take a couple minutes to pause this video here and solve this problem. Complete the ranking, complete the explanation. Everything we've said over the last 2 days should make this question pretty easy to answer, and when you hit play, we'll go over it. Okay, so your ranking here ends up being A is equal to C. So you could have put C is equal to A, then B, then D. And that should come as no surprise here, because notice, for these kind of problems, when they ask you to rank the time, based on everything that we've said so far, basically what you're ranking is the rotational inertia from least to greatest. And so the explanation for this one could look a little something like this. The object with the least rotational inertia will make it down the ramp in the least time. Since the radii are the same, the larger the fraction before the mr squared, the larger the rotational inertia. A smaller rotational inertia means that more of the initial gravitational potential energy will be converted into translational kinetic energy, which will allow the object to make it down the ramp the fastest. And we can also say here that it will have a higher average speed. Remember, as was stated in the video yesterday, or maybe it was the day before that, I'm having trouble remembering, but we definitely mentioned that when the AP test is talking about ranking times, they're going to want you to mention average speed at some point. The final speed plus the initial speed, which is 0, divided by 2 determines the average speed. So the highest final speed gives you the highest average speed. And of course, if the average speed is higher, since they're all traveling the same distance, and in the average speed equation, T equals D over V, a higher average speed gives you smaller time. Now, just as a secondary statement, although it's not that big of a deal, I think it probably should be noted that one of the tricks they tried to give you, I'll go back to that in a second, but one of the tricks they tried to give you was giving you 2 solid spheres, and one of them was 1 kilogram and one of them was 2 kilograms. They were trying to trick you here into ranking these as not being equal. It's important to mention the mass of the object has no effect on the time it takes to make it down the ramp. Because you could argue, well, if the mass is higher, then wouldn't the rotational inertia be higher? Sure. But the force of gravity acting on it is also higher. Those two have a sort of cancellation effect. Take a second to pause this video and write this down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, now there are a lot of good questions on this sheet. Number 2 is a great question. Number 3 is a great question. So is number 4. I actually want to jump to number 4 first, just because number 2 and number 3, whether you realize it or not, are actually really similar. So I want to jump to number 4 on the sheet. This is the last one. This is the one that's labeled as B6RT31. Objects moving down ramps, speed at bottom. It says here, in each case, a 1 kilogram object is released from rest on a ramp with a height of 2 meters from the bottom. All the spheres roll without slipping, and all of the blocks slide without friction. The ramps are identical in cases A and C. The ramps in cases B and D are identical, but not as steep as the others. It says here, rank the speed of the objects when they reach the horizontal surface at the bottoms of the ramps. And so basically that's once they've completed that full 2-meter drop. Take a second to pause this video here, come up with a ranking, come up with an explanation, and when you hit play, we'll go over it. All right, now everything we did with those 3 calculations talking about an object moving down that 30-centimeter ramp before should have given you enough information to be able to complete this question and rank it and explain it properly here. The ranking is B equals C, then A, then D. Now, the weird thing about the explanation for this, I think, is from a conservation of energy standpoint, the problem being described in cases B and C is kind of a totally different problem than the one being described in A to D. And so I think in some way, shape, or form, your explanation should address that. Notice I put here, since the gravitational potential energy for B and C is only converted to translational kinetic energy, the two blocks will make it to the bottom with the largest speeds. And those will be identical because, same height, same final speed. For A and D, the rotating objects, the gravitational potential energy will be converted to rotational and translational kinetic energy. This means the object with the smallest amount of rotational kinetic energy will have the largest translational kinetic energy, and thus the largest speed. Since the solid sphere has more mass concentrated closer to its pivot point, it has less rotational inertia, which means it will get down to the bottom of the ramp with a larger speed than the hollow sphere. Now, before I tell you to pause this here, I just want to point out, they could ask a question like this on the AP test too. Notice in this particular question, they didn't give us any information about how the rotational inertia of the solid sphere compares to the hollow sphere. You should recognize when something is hollow versus when something is solid, that the hollow thing is going to have a larger rotational inertia. And that's because when the object is hollow, it has more mass concentrated farther away from its pivot point, and as a result, it has a larger rotational inertia. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so I really just wanted to do the problems on the sheet together that were really similar. 1 and 4 are really similar, and 2 and 3 are really similar. So let's go to number 2. Number 2 on the sheet is labeled in the tipper's book as B6 QRT 29, solid sphere rolling along a track, location at highest point. A solid sphere rolls without slipping along a track, shaped as shown at right. It starts from rest at point A and is moving vertically when it leaves the track at point B. I'm going to say 2 things about this problem. Notice here they say it is moving vertically when it leaves the track. That means vertically only. The other thing I'll say as you're answering this question is remember the problem on the conservation of energy test with the alligators. The question says, at its highest point while in the air, will the sphere be above, below, or at the same height as point A? Explain your reasoning. Take a couple minutes to pause this video here and answer this question. And when you hit play, we'll go over it. Now, let's remember the alligator problem for a little bit. When we were doing the alligators on the conservation of energy test, we said the height can't possibly be the same because the object is moving sideways at its highest point. It has some kinetic energy there. And so that means, a lot of the kinetic energy that this object has is going to be converted back to gravitational potential energy, but not all of it. Now, this problem is different in a lot of ways, particularly because the object now was shot straight up in the air. And so it has no sideways kinetic energy, or I should say it has no kinetic energy associated with its sideways motion because it's just going straight up. The answer here is B. It's still below the highest point. The question is, why? It's pretty simple. If you want to test this on your own, take like a ruler or even a pen. Take a pen and throw it up in the air. Keep it flat in your hand when you're throwing it up. You'll notice it goes up, stops at its maximum height, and it comes back down. Then take the pen and hold it from one side and spin it while it's in the air. And watch what happens to the spin as it reaches its maximum height. If you're actually listening to me and doing this while I'm saying it, you should realize that when the pen reaches its maximum height, it's still spinning. Since there is no torque caused by gravity to slow the sphere down once it becomes airborne, the ball will still be rotating once it leaves the ramp. It never stops spinning. And so this means that some of the original gravitational potential energy will still be locked up as rotational kinetic energy, Locked up is obviously a weird word to use here, but that's the way I like to think about it. Because it's still spinning, you're never getting that energy back as gravitational potential energy, or at least you're never getting it back while it's still spinning. This means that when the translational kinetic energy is completely converted back to gravitational potential energy as it rises, the gravitational potential energy at the max height has to be less than the gravitational potential energy at point A, because some of that energy is still locked up in the rotation. It's being used to make the thing rotate. And that means there's less potential energy when it reaches its maximum height above point B. And that means it's going to be a lower height than whatever it was at point A. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And for the last problem on the sheet and the last problem for the day, we'll look at number 3 on this sheet, B6RT30. Moving down a ramp, maximum height on the other side of the ramp. It says, in each case, a 1 kilogram object is released from rest on a ramp at a height of 2 meters from the bottom. All the spheres roll without slipping, and the blocks slide without friction. This question says to rank the maximum height of the objects on the other side of the ramp. Weird question. Take a couple minutes to pause this video here and try to come up with a ranking, try to come up with an explanation, and when you hit play, we'll go over it. The question we have to ask here in order to answer this question is, why do the rotating objects rotate? And the reason why the rotating objects rotate is because friction puts a torque on the object and causes them to rotate. And so when they come down here, they are rotating clockwise. When they slide up the ramp, friction is going to be putting a torque on these objects. The difference is the torque on the way up the ramp is going to be opposite the direction of the angular velocity. When an object is on a ramp and it slows to a stop, it stops rotating. You can try this very easily if you take a pen without a cap and you roll it up something slanted in your house, like a book. Notice when you have the object rolling up the ramp and it reaches its maximum height, it actually stops rotating before it comes back down. Look at the logo, it stopped. And so because the object stops rotating, it doesn't have any rotational kinetic energy at its maximum height. And that means all of the gravitational potential energy that these objects all had, which was the same because the heights are all the same, that's going to be how much gravitational potential energy this thing has at the end. Now, it says here the blocks slide without friction, and it says the spheres roll without slipping. It's important to realize that rolls without slipping thing that we've seen in other problems is a very sketchy description. The reason why it's sketchy is because we say, for our purposes in this course, rolls without slipping means it's got enough friction to help the thing rotate, but not enough to take away any energy. And so the answer here says, since the object is on the ramp the whole time, the objects will stop rotating when they come to a stop. This means that all the kinetic energy, rotational and translational, will be converted back to gravitational potential energy. And this means all of the objects will reach the same height when they come to rest on the right side of the ramp. If you are thinking that this is confusing, I think that makes sense. But if you actually take a pen and you put it on a textbook and you roll the pen up the textbook, you will see that it actually does stop rotating when it gets to the top. And that's because there's a torque opposite the direction of its original rotation, and that makes it slow down. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, everybody, that is it for today. And with that, that is it for rotational energy. In our next video, we'll begin to talk about, well, the thing we talked about after energy. We talked about kinematics, we talked about forces, we talked about energy, then we talked about momentum. Next up is angular momentum, and that will close out the rotational motion unit. All right, everybody. Have a good one.